as we saw in the previous clip, if we want to understand the earliest times, the initial conditions, the beginning of our universe, we are forced to confront the structure of fundamental physics at the highest energies and the smallest scales. And for those of you interested, I thought I would give you a rather idiosyncratic and very imprecise introduction to the nature of these theories as they apply to the things that we were discussing. So this is certainly not a class in particle physics, although by training I am a particle physicist. That is actually what I know. This is going to be an impressionistic version of particle physics that will cover those aspects and try to make my kind of sense of those aspects that are relevant to our discussion of cosmology. So the version of quantum mechanics that is useful for describing relativistic particles is quantum field theory. And I want to motivate a little bit what that has to do with anything. In the context of relativistic theories of particles, one has to come to grips with the fact that particles can be created and annihilated. So you cannot study the motion of a particle and then do the quantum version of the motion of a particle through wave functions. You have to address the fact that particles can be created and annihilated. We already have a precedent for particles that can be and are created and annihilated, and their numbers change, and we deal with that quite readily in the context of photons. Photons are particles which are created and annihilated, and the way we discuss them is through an understanding of the electromagnetic field. And we have these two pictures of electromagnetism. On the one hand, we have the idea of an electric field and the fluctuations in the electric field. A wave, an electromagnetic wave, can be represented as a beam of photons. And these two pictures, the particle picture and the field picture, are what we are going to generalize to other particles. So if you want to describe a theory that allows for the creation and annihilation, say, of electrons, you introduce something called the electron field. Like the electric field, it has a value at every point in space-time. Now, the electric field is what we call a vector field because it's like the electric field. It points in a particular direction in space. And this is reflected in the fact that the photon, the particle associated to that field, is a vector particle. It has what we call intrinsic angular momentum, or spin, of 1. Now, an electron is a different kind of object. It, too, has an intrinsic angular momentum. It has a half a quantum unit of angular momentum. So the field that is associated to the electron field, is a spin 1/2 field. It, too, has some direction in space, but the way it is associated to that direction is somewhat different. It is a spinner rather than a vector. I can't go into that many of the details of what that entails, but it is associated to a particular direction. It is also true that electrons are fermions. They satisfy the Pauli exclusion principle. This too is reflected in the properties of the electron field. Once you get through to this, you have the understanding of particles are just excitations in some field theory. So there's some dynamical system, which we then quantize, and the excitation, the waves, the wiggles in the electron field are what we call electrons, in the same way that wiggles in the electric field are what we call photons. And the wave equations that describe these waves can be linear, in which case waves just propagate. Those are called free particles. And you can add nonlinear terms to these equations, which allow the waves to interact, and these interactions lead to interactions between the particles. And these interactions, because they're nonlinear, allow for particles to be created and annihilated, and if you write the correct interactions, then these creation-annihilation processes satisfy all of the conservation laws, because you build those into the interactions so that the interactions respect them, the symmetries associated to those conservation laws. This is a general story about quantum field theory. The specific kinds of quantum field theories that turn out to describe our universe turn out to be a rather restricted class of all possible quantum field theories, of which there's an infinite family. The standard model of particle physics involves particles that are in fact all fermions. The leptons, the electron, the muon, and the tau, along with their attendant neutrinos, which are also fermions. And then the constituents of protons and pions and neutrons and all the other excited hadrons turn out to be a collection of 6 spin 1/2 fermions called quarks. We'll discuss those in a moment. And all of the three forces of nature, I should say, gravity is not part of the standard model of physics. We'll get to that in a later clip. The three forces of nature are attributed to interaction with vector fields, like the electromagnetic field, so that the interaction of an electron with another electron through the electric field that repels them is understood as an interaction of one electron with the ambient electromagnetic field, the photon field that lives around them, and the interaction of that photon field with the other electron. Note that this naturally takes into account the relativistic fact that an electron over here can't know about what an electron over here is doing faster than the speed of light. An electron here moving produces a ripple in the electric field, which later moves this electron there. A similar phenomenon describes, for example, the weak interaction as an exchange of a different kind of vector boson, a W or a Z boson. We'll discuss their properties momentarily. And again, a ripple over a motion by some weakly interacting particle over here sends a ripple that propagates and transmits the information to some other weakly interacting particle. And we encode the quantum calculation of physical properties in these sort of graphic tools. We call them Feynman diagrams. On occasion, one can read these Feynman diagrams as though they were actually stories of what happened in the universe. It is possible to get very confused if you take them too literally. Feynman was bright enough to both take them literally and keep his understanding and his insight solid, but most of us are not Richard Feynman. It is important to remember that behind all this graphical mumbo-jumbo is a solid and concrete quantum mechanical calculation, for which these diagrams are coding for the way we are doing the calculation. That said, let's look at what these diagrams look like and misread them pretending we're as bright as Feynman. So this diagram over here describes the interaction of two electrons, and the idea is that an electron can emit a photon, and this electron over here on the right emits a photon, and that photon is absorbed by the electron over here. The photon carries momentum so that when it emits, this electron emits it, it recoils. When this electron absorbs that momentum, it too recoils, and we have a repellent interaction between the two photons. In these diagrams, time is to be read as moving up in the conventions done here. The photon in question is virtual. Those are details we don't need to worry about. Notice that already you see that something is confusing. This works well for an electron and an electron. What if there were an electron and a positron involved? Well, they still would interact by exchanging photons, except this time the interaction is attractive. This is less like throwing a medicine ball and recoiling. In this case, the emission of the photon would cause the electron to deflect towards the positron. Clearly, one has to exercise care not to take these things too literally. The interactions, we're doing a sort of expansion in the case that the interactions are weak. This is justified in the case of electromagnetism, for example. And so each time that an electron emits a photon or absorbs a photon comes with a factor of essentially the electron charge. And the electron charge is a small number, not because it's a small number of coulombs, but there's an intrinsic measure of the electron charge, which is associated to the square of the electron charge divided by hc, which is about a 1/100th. And so we're doing an expansion in this small parameter. And so, for example, this diagram is part of codes for part of a concrete calculation of the scattering amplitude, the probability that two electrons shot at each other will interact, and this reflects the repelling force between them. You can do the same calculation with a positron. The values that come out would be slightly different, and they would represent the attractive force between an electron and a positron, and we can use these to make such calculations. So we have the photon that mediates the electromagnetic interaction. What else do we have? Well, we build the standard model of particle physics, as I suggested, out of a collection of 6 quarks, up, charm, top, down, strange, and bottom. Some people used to call top and bottom truth and beauty, but I think top and bottom have become the standard names. You see in this table their masses. You see that the masses increase to the right from about 2 MeV for the up quark all the way down to on the order of 170 GeV, billion electron volts over c squared, for the top quark, so the top quark being the most massive, the most difficult to create, you need to focus a lot of energy in one place, is the most recently discovered one. I would point your attention to their charges. The charges are somewhat strange. The up charm and top quark have a charge of 2/3. The down, strange, and bottom have a charge of -1/3. Who ever heard of a particle with 1/3 of the electron charge? Nobody, for good reason. There are no particles in nature with fractional charges. But Ronan, you have a whole table of particles with fractional charges. Yes, these particles, these quarks, are never detected. These quarks are very interesting. In addition to their names, their flavors, we call them, an up quark or a down quark, which determines their mass and their charge. These quarks come, in some sense, each of them in 3 varieties. We call them colors because there are 3 of them. So an up quark can be a red up quark, a green up quark, or a blue up quark. Of course, these are not real colors. They have nothing to do with optics. But they are 3, roughly, kinds of up quarks, 3 kinds of charm quarks, 3 kinds, so on and so forth. And of course, with all of these come their antiparticles. So there is an anti-green, anti-U quark, and an anti-blue, maybe you'd call anti-blue yellow, an anti-green magenta, an anti-red, whatever the teal is that goes with that, cyan. And so there are 3 colors of quarks and 3 colors of antiquarks. And color, it turns out, is the charge that is responsible for the strong force. The vector boson that carries the strong force are these gluons. Gluons come in color-anticolor combinations, and if you think about it, there are 9 color-anticolor combinations. One of them is irrelevant for reasons that I won't discuss. So there are actually 8 different massless vector bosons that are called the gluons. And for example, the interaction shown here conserves color in the sense that a green quark, maybe an up quark, emits a green anti-blue gluon, turning into a blue quark. So both green and blue color are conserved here, and that green anti-blue gluon can be absorbed by a blue gluon quark that turns it into a green quark. So you see that this conserves color in the same way that this conserves electric charge. Notice that unlike the photon, which is a neutral particle, so does not itself carry an electromagnetic field, the gluons are colored, so they themselves carry color fields. Quantum chromodynamics, the theory of color, unlike quantum electrodynamics, the theory of electromagnetism, is nonlinear in almost as horrible a way as general relativity. Remember, in GR, it was the fact that gravitational waves or gravitational fields carried energy and therefore gravitated, which made the theory nonlinear. A similar phenomenon is going on here. Gluons are colored, so they carry color. Now, it is a property of the color interactions that color is confined. There are no colored particles observed in nature. We have never seen a quark. We have never seen a gluon. We observe or deduce their existence indirectly, but at low energies, there are no quarks and there are no gluons. In fact, color, this nonlinear interaction causes a phenomenon called confinement that states that all of the particles that we see in nature are in fact color neutral. What does that mean? Well, that means, for example, that one can build a particle out of 2 up quarks and a down quark. You remember that the charge of an up quark is 2/3, and the charge of a down quark is -1/3. So this is a particle with total charge 2/3 plus 2/3 minus 1/3. That's a particle of total charge 1. In fact, this is a proton. So a proton is a bound state in QCD of 2 up quarks and a down quark. You can convince yourself that replacing one of the up quarks by a down quark, you find a neutron. And notice that when we build this proton, if one of the up quarks is blue, if one of the quarks is blue, one must be red and one must be green, so that together the combination is colorless. And so, in fact, all known hadrons, modulo some exotics that maybe have been discovered this past 2 years, are bound states of 3 quarks. The proton, the neutron, and all the excited hadrons that we know are formed out of combinations of 3 quarks such that they are color neutral, and you can convince yourself that any combination of 3 quarks has an integral charge, so that works. There are also, so these are hadrons, the heavier, strongly interacting particles. And then there's another way to make integral charge and color neutral combinations, which is to take a quark and an antiquark. So if you look at this particle, it's got an up quark of charge 2/3 and an anti-down quark of charge plus 1/3. This also has charge plus 1. This is the positively charged pi meson. And again, if you reverse the role of up and down, you have an anti-up and a down, you get the pi minus, and then some combination of up, anti-up, and down, anti-up. Down, anti-down would be pi 0, and the other would be another meson called eta 0. And so quark-antiquark combinations can be integrally charged. And notice this is also color neutral. We have a blue up quark and a yellow anti-down quark. So anti-blue, and again, this whole combination is color neutral. Color is confined so that all particles in nature are color neutral, and this leads very nicely to predicting all of the different kinds of baryons and all of their interactions. Now, one thing that's weird, of course, is that this is baryons. Together, baryons and mesons are hadrons, and I'm tired. Now, one of the interesting properties is that a proton is color neutral. Neutron is color neutral. I said that they interact through the strong force, and the strong force is carried by gluons. Why do these objects interact at all? One way to think about it is that the strong nuclear force that incredibly powerful force that binds nucleons inside a nucleus is the tidal remnant of an overall neutral proton and an overall color neutral neutron that can still attract each other through tidal interactions, through sort of some of the color on one side of the proton interacting with some of the color on another side of the neutron. It turns out that an effective description of this can be given. This was discovered long before quarks and color were known by Yukawa as if the force between nucleons was mediated by the exchange not of a vector boson, but of a scalar boson, in fact, this very pion. So the pions were conjectured as the scalar particles exchanged between nucleons, generating the strong interaction, and then what was discovered was the muon, which was first thought to be that particle, but it had the right mass, roughly, but the wrong properties, and subsequently the actual pions were discovered. A famous physicist, when told about the muon and its failure to be Yukawa's meson, once quipped, who ordered that? So we have this picture of the strong interaction as the exchange of these gluons, and I said the property of this nonlinearity is that color is confined. And what that means, in effect, is that if you take a pion, and imagine you had a very small, powerful pair of tweezers, and you took this up quark and anti-down quark and pulled them apart. Well, the color field between these two particles, when they're separated, is not, you don't get sort of like the analog of the electromagnetic field over all of space. The color field is concentrated in what's called a flux tube between them, a sort of string between them. And the string has a constant energy per unit length, a constant tension. It's like a rubber band in the sense that when you extend it, you have to put energy into it because you're pulling against the rubber band. Now, if you caught these two things with a pair of tweezers and tried to separate them, you would have to apply a constant force. As you got the farther, a constant force. The force is not getting stronger. It's not like a Hooke's law spring, some kind of weird spring, where the energy is linear with distance. So if you tried to separate a quark and an antiquark, what would happen that make up a pion eventually is that you had put so much energy into this rubber band, into this flux tube, that there's enough energy there to pop out of the vacuum, say, up, anti-up quark pair. That together is uncharged. It doesn't violate any conservation laws. And you would find that in one hand you're holding an up anti-up particle, a combination of an eta meson and a pi 0, and in the other hand you're holding an anti-down up meson, the pi plus. So when you try to break up a pion, what you end up with is not two quarks, but two mesons. And this is really what happens when you try to stretch a rubber band. You try to stretch a rubber band too much, you end up with two rubber bands and four ends. So quarks are like the ends of strings. This might be important in later discussions. But this is where we don't see quarks. This nonlinearity has another property, though, that if you measure the interaction between quarks and gluons, it depends on the energy at which you measure it. I'm not going to explain why that is. And at higher and higher energies, the interaction is weaker and weaker. What this means is that at low energies, when you try to pull the quarks apart, there's a huge amount of energy invested. But if you whack at them very hard, they behave almost as though they were free. This property is called asymptotic freedom, and it is a very important property. This is what led to the fact that at high energies, when we heated a combination of nucleons, effectively they melted and fell apart into this strongly interacting plasma of quarks and gluons. So at high energies, quarks are asymptotically free. At low energies, they are confined. Interesting. We talked about electromagnetism. We talked about the strong interaction. What about the weak interaction? Well, the bosons that mediate the weak interaction are strange. They're called the W and Z bosons. They, first of all, carry electric charge. The Z is neutral. The W plus and W minus carry electric charges. This means that the exchange of a W minus, for example, can cause a neutron to change into a proton. Fundamentally, there's one of the quarks, in fact, a down quark, changing into an up quark, and that changes a neutron into a proton. But if you look at this process, this is the decay of a neutron. A neutron decays to a proton, an electron, and an antineutrino by emitting a W boson, and the W boson decays to the electron and the antineutrino. You can see that that conserves all of the charges at each one of these two vertices. I should point out that one of the properties, I said, remember that we expand in this small parameter, 1 over 100, for the weak interaction. The same kind of expansion for the strong interaction is kind of a problem because at low energies, the effective value of this parameter is about 13, and expanding in a power series in 13 is a bad idea. However, at high energies, the calculations of by Feynman diagrams and QCD are very effective. At low energies, we need to find other methods to solve QCD, and that's still a very ongoing research program. The weak interactions are weak, so the perturbative calculation works. In a sense, the fact that these bosons, the W and Z, differ from the massless gluons and photon by the fact that they are massive. They're in fact quite massive. If you notice, the Z has a mass of about 90 GeV, and the W's a mass of about 80 GeV. This is tightly bound to the fact that the weak interaction is a short-range interaction, but we won't go there. The quarks undergo weak interactions. So do the leptons. Here down, we're completing our table of particles, again arranged in order of increasing mass to the right. The electron, muon, and tau meson, and the corresponding neutrinos, and everybody comes with their own antiparticle, as discussed. Now, the short-range interaction mediated by the massive gauge bosons is all very nice, but as was known in the 70s, this cannot be the fundamental total theory of the weak interactions. Something is wrong with this theory. In order to explain what it is that's wrong with it, well, I won't, but I will say something about it. I want to go back to thinking about these Feynman diagrams and what they code for, and I want to introduce a word that is often thrown about and I think badly misunderstood. The concept I want to talk about is renormalization. So, renormalization. So we drew the diagram that we started with, this sort of Feynman diagram that coded for one of the contributions to the scattering of an electron off of another electron. Remember, time flows up, so we have 2 electrons coming in and then 2 electrons coming out, and this is a contribution to electron-electron scattering, and there are other more elaborate diagrams, and you add them up and you compute to arbitrary accuracy. Great. For example, so you can compute the cross-section for electron-electron scattering. For example, the electron-photon cross-section, this Thomson or Compton cross-section that we computed. So wavy lines here indicate photons, lines with arrows indicate electrons, and you can imagine a photon meeting an electron. You can insert the vertex that I described, and you see that a photon and an electron come in, a photon and an electron come out. So this is the scattering of a photon off of an electron. And you can compute the Thomson cross-section from a process like this, from summing diagrams of this form. Great. Now I want to draw another kind of diagram. In this case, the incoming particle is just an electron. The outgoing particle is just an electron. So certainly nothing is being scattered here. But I can, with two vertices, have a wavy line that is a photon that this electron emits. And of course, when it emits a photon, it continues as an electron. So this is the same electron emitting a photon and then reabsorbing it. Now, so this is the scattering of an electron off itself. What does that mean? Well, when you interpret the diagram correctly, it turns out that this diagram is a contribution to the mass of an electron, a correction to the electron mass. Well, great. What does this mass do? Well, remember, each vertex comes with a factor of e, so this is proportional to e squared. And then you can compute the coefficient, and the coefficient comes out to be infinity. So this diagram, the quantum calculation associated to this, leads to an infinite answer for the correction at first order to the mass of the electron. What does this mean? Infinity, physics is not infinite. When you get infinity in physics, you're doing something wrong. Indeed, we are. The process that reminds us what we should be doing is called renormalization, and it's often dressed up as a way to sort of cancel infinities and add 1 plus 2 plus 3 plus 4 and get minus a 12th. There's nothing mystical about it. Renormalization just reminds us that if you get an infinite answer, you were asking a stupid question. What was stupid about this question? And I want to emphasize this. What we were really doing in setting up the calculation, the way that gives us this crazy infinite answer, and I should indicate that, well, in this case it's a little more complicated, but where the infinity comes from is a region in the calculation of this diagram where these two interactions occur at exactly the same point in space and time. It's that region called the deep ultraviolet, very short distance, in which there is a divergence. Now, what does this really mean? Well, the silly calculation we were trying to do is we were trying to imagine the following picture. Imagine an electron that doesn't interact with the electromagnetic field. So it doesn't have a charge, a neutral electron. Then introduce the interaction to the electromagnetic field, one bit at a time, and then compute how the mass of that electron changes. What we found is that that would be an infinite contribution, but that's not surprising. An electron is a charged particle. It fills space. If you have an electron, it fills space with its electric field at large distances and also all the way at short distances. An electron, as far as we know, is a point particle. The 1 over r squared dependence of the electric field means there's a very intense field very close to the origin, and the energy in that field is infinite. This was known in the 19th century. The reason we got an infinite answer is because we were asking a dumb question. We were asking, what's the difference between the mass of an electron without electric fields and a mass electron with electric fields? That's not a physical question because in the universe there are no electrons without electric fields. If you correctly express the mass of the charged electron, plug that back into your calculation and express all of these scattering probabilities in terms of the physical mass, there is and never was anything infinite about your calculation. So renormalization is not a way of hiding the infinities, it's a way of realizing that in physics there are no divergences, no honest divergences. A divergence means you've neglected something. We'll see that in the sequel. Let's try one other diagram that I can draw. In this case, there is no incoming particle and no outgoing particle. Nothing is scattering at all, but I'm going to still have two of those vertices where an electron emits a photon and absorbs a photon, but this time it's biting its own tail. So what does this process contribute? This process too, by the way, if you naively compute it, turns out to be proportional to e squared times infinity. So, redrawing it more neatly, to what does this process make a contribution that appears to be infinite? Well, it's certainly not any kind of scattering process. There's no incoming or outgoing particle. And indeed, what this process is indicating a divergent contribution to turns out to be the vacuum energy density. So you ask, that's a physical question. Does this mean that in electromagnetism the vacuum energy density is infinite? Well, it turns out that here life begins to be complicated. This does look like a divergent calculation. If the universe were made up only of electrons and photons, then this does predict, in some sense, an infinite vacuum energy. Of course, in this approximation, we don't have to worry about it, because when we're doing quantum field theory, shifting the energy of the vacuum is an irrelevancy. If I tell you that the universe that has an energy of 100 joules, or I tell you the universe has an energy, or this room has an energy of 1 billion joules in its vacuum, this is an irrelevancy. It just shifts all energies by a constant, up and down. And we know that shifting all energies by a constant is irrelevant, or what you call energy zero. We've shifted it around several times over the course of the class. Only energy differences are meaningful. Since there's no way to mine the energy out of the vacuum, who cares what the energy of the vacuum is? This is, of course, not true when you're doing gravitational theories. There, the energy of the vacuum is meaningful. So now we might want to look at this more closely. And it turns out that indeed, what causes the actual physical energy density that contributed by electrons and photons not to be infinite is that at high energies, there is more than electrons and photons in the universe. There are W bosons, there's the weak interaction. That, it turns out, tames to some extent this infinity. Now, as I said, we do not actually get a finite answer when we sum up all the particles, but one can imagine that, again, since the divergence is in the extreme ultraviolet, when these 2 points are at the same point in space-time, there may be additional particles that we have never heard of in the ultraviolet that tame this infinity. So in a complete theory of the universe, that we'd expect the vacuum energy to be finite, because these particles would be relevant when these 2 points were distances of order their mass, or their mass converted to distance units. This led to our prediction that if the next, at the end, what tames the infinity is something of whose mass is the Planck mass, then you expect a vacuum energy of order the Planck mass to the fourth, and this is why we said there's a problem with the cosmological constant. So this is renormalization. Other than the vacuum energy, which in most applications of quantum field theory is irrelevant, there are no infinities to hide. There just are no infinities unless you ask silly questions. What has all this got to do with the electroweak interaction, which is what I was trying to say? The point is that this renormalization program shows us that a theory with massive vector bosons is not renormalizable. Its high energy, ultraviolet behavior is non-renormalizable. It cannot be a fundamental theory of the universe. This was realized in the 70s, and the solution, the creative solution that physicists came up with in the 70s is what's called the Higgs mechanism. You imagine starting with a theory which has bigger symmetry and has massless W and Z bosons and a massless photon. And it turns out, in addition, massless electrons and leptons and quarks, and all of the particles are massless. In this symmetric theory now, just like electromagnetism or just like quantum chromodynamics, this theory is renormalizable and does make sense. How do you explain that at low energies we observe massive particles? Well, you imagine that in this theory there is another field you have to add. It's called the Higgs field, after Peter Higgs, who formulated the idea. And this Higgs field is a field that is charged under the electroweak interaction, that is the unified interaction proposed by Glashow, Weinberg, and Salam at high energies. And at low energies, what happens is that this field acquires a non-zero value. Just like you can have a non-zero electric field, you can have a non-zero Higgs field. Now, the problem is that a non-zero Higgs field, remember the Higgs field is a scalar. That means it does not ruin isotropy of space. If you had a non-zero electric field, you'd have isotropy problems. A non-zero Higgs field doesn't point in any direction in space, so it doesn't ruin isotropy. But there is an internal Higgs space on which the symmetry that was associated to the masslessness of the W and Z bosons acts. And it does break that internal symmetry. There is not a symmetry that acts on space, but some internal symmetry, kind of like electron number, though not exactly electron number. And the breaking of that symmetry allows us to, at low energies, observe, on the one hand, a massless photon, and on the other hand, massive W and Z bosons, and the interaction with this everywhere existing Higgs field is what leads to the masses of the quarks and the leptons, although, as others will note, not to the main contribution to the mass of a proton, which is either to be thought of as the kinetic energy or the energy in the glue field between the quarks. One of the properties of this Higgs field is that, this is an example, which is not exactly the Higgs field that we see, but a variant, where you see that the symmetry in this case is, in this internal fake space, this is not space, this is field space if you want. There is a symmetry under rotation, and the potential is such that when the Higgs field locates a minimum, there is a whole ring of possible minima. Now all of these are related by a symmetry, they're all the same vacuum. But when the Higgs field acquires some value, say it picks this value, now the choice of that value breaks the symmetry. So the expectation value, the value of the Higgs field breaks the symmetry. What we note is that then the Higgs field, like every field, codes for particles. There are two kinds of particles coded for by this Higgs field. One corresponds to fluctuations of the Higgs field back and forth in this direction. Since all of these directions are exactly the same, that's not really a particle. This would be a massless particle, and there is no massless Higgs particle. So these fluctuations do not exist. And this particle is non-physical. On the other hand, there are the perturbations in the direction perpendicular to this ring, so up and down the sides of this potential. That corresponds to a massive particle. That particle does exist, is predicted to need to exist, along with exactly what its couplings are, from the fact that it is associated by this sort of transverse versus longitudinal relation to the field that breaks the symmetry. And the fluctuations in this direction are the Higgs boson that was discovered last year. So it is in this sense that deep considerations of quantum field theory and normalizability predicted the existence of a Higgs boson in order to make the weak interactions consistent. And so that is why those physicists from the 70s were so gratified to actually find the Higgs boson discovered. It was a triumph of quantum field theory. The last thing to point out, because it'll come up later, is that at high temperatures, quantum fluctuations or thermal fluctuations make, if the temperature K Boltzmann T is much higher than the depth of this well, then the little dimple at the bottom of this parabolic potential or quartic potential is completely irrelevant, and we might as well replace it by this, and the Higgs field can be very happily zero, and this is what you see as the effective potential at high temperatures. As you lower the temperature, this becomes relevant, and so at high temperatures, the world lives in a symmetric phase, and there is a phase transition where the symmetry is broken as you cool the world down below 100 GeV in energy, and it is in this transition that the Higgs field acquires an expectation value. If you could trap the world with the Higgs field at zero at low energy, then the height of this potential would measure an energy density, a cosmological constant, if you will, of that universe. This, it turns out, is not the cosmological constant we measure, nor is it probably the inflaton field that we will talk about later in the week, but it gives you sort of analogous scalar particles in other theories will be able to fulfill precisely that role. So I don't think I have actually taught you quantum field theory, but perhaps I've given you my own idiosyncratic approach to some of the concepts as they arise in discussing cosmology. I hope you found it useful.